So next up is Alex Ray. He is the owner and lead consultant for Payette Environmental Services in McCall, Idaho. Before starting his own business, Alex spent over 15 years working for federal land management agencies across the Western US. And what he really specializes in is that intersection between the recreation and aquatic resources. And he holds a master's environmental degree with Western Colorado University. So with that, as Alex is going to go ahead and share his screen, and a reminder again, just use the Q&A chat box, and we'll try and get to as many questions as possible.
Great.
All right.
Thank you all very much. And can you all hear me okay?
Yes.
Well, I'd like to thank you all for joining me today. As Julia said, my name is Alex Ray, and I live in McCall, Idaho. Today, I'm actually joining you from the hill country of Texas. I conducted the research I'm about to present to you in pursuit of my master's degree in environmental management with Western Colorado University, and much of the work I conducted in the summers of 2019 and 2020. I chose this topic as my thesis project because of both my professional and personal interests in recreation management and water resources, and also because it concerns a resource close to my home and right in my backyard. Before I get started, I want to thank Brian for the previous presentation. That was one of the best, most informative speeches on waves that I've ever seen for a layman audience, and it really provides some crucial background for the information and the research that I'm about to give to you. So, defining no wake zones for wake surf boats, a data-driven approach. First, as a little background, I want to talk to you about Payette Lake and where this research took place. Payette Lake lies in the heart of central Idaho, and it's a north-south oriented oligotrophic glacial lake. I believe this is very similar to a lot of the lakes you have up there in the Great Lakes region. Much of the southwest basin of the lake is ringed by development, both commercial and residential. The peninsula of the lake is actually a state park, Ponderosa State Park. And when you come back around to Pilgrim Cove on the eastern bay of the lake, it's residential development all the way up to Paradise Point. Around the north end of the lake is state park land again and some state endowment lands. And some of the west side of the lake there by the Narrows and just west of Cougar Island is also state land, state endowment lands. So like a lot of these lakes, it supports a huge recreation economy, motorized and non-motorized, fishing, you name it. And then in the winter, it freezes over and it supports snowmobiling, skiing, and a little bit of ice fishing even. It's approximately 5,000 acres, max depth of 300 feet, a catchment basin of 144 square miles, and the residence time of water in the lake is 2.35 years. It's approximately 6 miles long, and in the widest area there in the Southwest Basin, it's just over a mile wide. Importantly, it's the source of McCall's drinking water. So a lot of this research was conducted in an effort to look at sustainable and resilient futures for McCall and how can we protect the resources that concern everyone, including the drinking water. So like many lakes across the country, in recent years, in the past 5 to 10 years, we've seen a huge increase in motorized recreation. A lot of this also has come in the form of wake boats. There's over 300 docks, private docks ringing the lake, and we have a couple marinas. There's boat rental agencies in town and in the closest big city 100 miles away, and we get pretty heavy wake surf boat traffic. Because of this increase in use, there's been a lot of questions about what impacts these wake boats are causing, and anecdotal evidence has already shown there's been shoreline erosion and lakeshore infrastructure damage. So a lot of the members of the community have been asking, what are the potential impacts? What are the impacts we're seeing, and what can we do to mitigate these impacts? Nutrient loading has always been somewhat of a problem in Payette Lake. This is partially due to the low water residence time in the lake and shoreline development that's been going on since the early to mid 1900s. A 1997 study by Paul Woods of the USGS titled "The Eutrophication Potential of Payette Lake" made a number of important observations regarding nutrient loading in the lake. He found landscape scale fires in 1994 contributed heavily to phosphorus and nitrogen loading in lake bed sediments. He also found that lake bed sediments in the southwest basin of the lake contained especially elevated levels of phosphorus compared to other areas of the lake. This is important because that southwest basin is the most heavily developed and is the most heavily trafficked. A third finding he found was that substantial hypolimnetic dissolved oxygen deficits with development of anoxia constituted strong symptomatic evidence that Payette Lake had undergone eutrophication. So this last finding was important and it was under-recognized, and many people don't know this. Even in the report, Paul Woods noted that a better title for this paper would have been, "Can eutrophication of Payette Lake be reversed?" With the algal growth that we were seeing and the low oxygen levels, it was definitely on its way to eutrophication. However, we haven't seen the type of conditions typically associated with eutrophication, large algae blooms, very turbid water, anoxic water, but small cyanobacteria blooms have occurred in the last few years. Other reservoirs in our county, other lakes and reservoirs, Cascade Reservoir in particular, experiences pretty severe algae blooms every summer, and recreation has to be shut down in the lake. And many other lakes in the area are affected by cyanobacteria blooms. The threat exists in the area, and especially with the potential for aquatic invasive species dispersal heightened by motorized recreation, it's become really important to try and see how we can keep these blooms out of Payette Lake. So, because these blooms can also be associated with motorized recreation in the form of lakeshore and lake bed sediment disturbance, I kind of tried to set out to determine if there was a link between the two in Payette Lake and where kind of that intersection is. To do so, I focused on 3 questions, all of which conveniently help delineate an effective no wake zone for the lake. And they also informed us about present conditions in the lake and what we could look at moving forward. So my 3 primary questions were, what are the potential effects of motorized watercraft, and specifically wake source boats, on shoreline and nearshore sediments? Is the 300-foot no wake zone currently in effect in Payette Lake sufficient to protect environmental and economic resources in the lake? And how can data be employed to effectively delineate no wake zones for wake surf boats? Looking at these 3 questions, it became clear that there were 3 pretty major areas of study I needed to look at. I needed to analyze wind wave regimes on Payette Lake to get a good feel for what baseline conditions look like, what baseline wave conditions look like, and what baseline erosion may look like at the lake shore. Next, I measured surface waves from wake boats and other motorized wake watercraft just to prove once again that wake boats do make larger waves than other motorized watercraft, and 2, in our case, that they're making larger waves than we would see from the background wind noise on the lake. The final thing I did was I modeled the depth influence of wake boat slipstreams. The slipstream is the jet of water that comes off of the propeller, and this has the potential to affect bottom sediments at substantial depths. Research conducted on outboard motor boats in the 80s and 90s showed that even those boats could affect sediments up to 3 and 5 meters. And with the development in motor design and the new V-drive motors and the increase in horsepower in these boats, it's become apparent that the depth influence of these slipstreams may be way more substantial than previously thought. So the first area of study, the wind wave analysis. Brian talked a lot about this, how we look at wind waves by the fetch, by the duration of the wind, the water depth, and other parameters. Payette Lake, because it's pretty narrow, is considered fetch limited. The predominant wind blows to the east or to the south, and this mainly affects the Southwest Basin because it has the largest area of fetch in it. I measured wind speeds in those areas. I deployed 2 wind speed sensors in the Southwest Basin in 2019 and 2020. And I took nearly 6 months of data during the summer ice-free months. For the rest of that time period, I analyzed data from the airport, which was collected by NOAA and made publicly available. And through all this data, I just looked at what do average wind speeds look like, what does a typical storm event look like, and what do strong storm event and gust speeds look like. In reality, the duration of the wind speed is not that strong. It rarely blew with a solid duration for more than an hour or two, either at the airport or across the lake. And because of the low fetch, this means that waves can only grow to a certain size. In this sense, as I said, Payette Lake is considered fetch limited. These 4 graphs right here show the wind wave height on a 1 kilometer fetch for a 1 hour duration and a 1 kilometer fetch for a 2 hour duration, as well as a 2.5 kilometer fetch for a 1 hour duration and a 2.5 kilometer fetch for a 2 hour duration. These are common durations of wind and common fetches that we see on the Payette Lake. And as you can see, all 4 graphs are almost exactly identical. The 1 kilometer fetch, regardless of the duration, the wave height stays the same. And with the 2.5 kilometer fetch, regardless of wind duration, the wave height stays the same. So on the right there, you can see some of the readouts from the wind wave analysis I took, and you can see that it's long periods of calm punctuated by some rather windy or some storm events. I was able to measure these wind waves also as part of my boat wake measurement, and this corroborated a lot of the data that we saw from modeling. So modeling and direct measurement revealed that the average height of waves on Payette Lake during a normal wind regime day is 2 to 4 inches. Typical storm events on the lake can produce waves up to 8 inches high, and wind conditions may occur at times that produces waves up to 12 inches high. It's unlikely, based on the data I've seen and the conditions in the lake, that we would see natural wind waves more than 12 inches high. One thing that's important about this.
Hey, Alex, just one quick thing. Just a couple times, a lot of times, I don't know if you're moving papers or something, it's coming through as background noise for a lot of people. Just wanted you to be aware of that.
Okay. Yeah, I'm not sure.
Okay. Just wanted you to be aware. Thanks.
Okay. And finally, one of the important conclusions of the wind wave analysis is that the wavelength of wind waves is significantly shorter than similar height waves created by motorized watercraft. As Brian just explained to you, waves affect not only the surface, but they affect the depth of the water column. This means that the wind waves really aren't affecting too deep in the water column as they approach shore, and especially when you compare them to the larger waves created by motorized watercraft. So for the next part of my study, I looked at actual surface waves from motorized watercraft. To measure these waves, I used a Global Water WL16 submersible water logger with an automatic barometric pressure compensation, and I had it programmed to read 10 times per second. I deployed the water logger from 5 to 10 meters of water just offshore in some areas with pretty resilient, rocky, and steep shorelines. I did this in numerous places around the lake, and I captured similar data from numerous places as far as wave height. So I don't suspect that refraction off of the rock wall behind me caused significant deterioration of the wave heights as they approach, but that is a possibility on this data. I did do some controlled testing of wake surf boats operating at different, at set distances from the water logger. However, environmental conditions and other boats on the lake kind of negated the usefulness of some of this data. There was just too much background and noise involved in it. A lot of the really good data I got from random sampling. I went out on a couple busy weekends around the 4th of July. I was able to deploy my water logger in about 6 meters of water in a pretty heavily trafficked area. I was able to record and timestamp boat passages and record their distance from shore with a digital rangefinder. And I categorized the speed of the boat as whether it was by whether it was towing a surfer or a tuber or a boarder, or if it was just operating at no wake speed, or if it was operating in planing speed. A few water ski boats did come by that were operating rather fast. So I collected many, many hours of data out there and did come up with some very useful data points, especially regarding wake surf boats. Some of the key findings I got here were that a wake boat operating at the 300-foot no wake zone boundary produced a wave that was 7.75 inches high when it reached shore. As you can see from the wind wave analysis, this is significantly larger than the wind waves that are reaching shore. And you can even see that in the wave data I collected on this day. And that's a boat operating fully legally at the 300-foot no wake zone boundary. During the day on July 3rd, the busiest day I was out there, nearly 30% of boats were operating, creating a wake within the 300-foot no wake zone boundary. I was able to capture a wake boat operating 135 feet from shore, and a surfer surfing behind this wake boat, and it produced a wave that was 9 inches high when it reached shore. So as I said with wind waves with the way shorter wavelength, due to the greater height and wavelength of waves produced by motorboats, surface waves carry far more energy than wind waves on Payette Lake. I did not attempt to calculate wave energy for any of the waves that I looked at. As Brian noted, that's a very it's a very difficult thing to do when you're looking at all these parameters, and there hasn't been a lot of good models developed to this point to compare those two different kinds of waves. It has been done. Gregor McFarlane with the University of Tasmania has been working on that and has produced some really great info from the Willamette River. But calculating this wave energy is still kind of in the preliminary stages of research in this field. Fortunately for these surface wake boats and this data I collected, the results were consistent with data collected by researchers with the University of Quebec in 2014 and the University of Tasmania in 2018. That was Dr. Gregor McFarlane on the Willamette River in Oregon. One of the key conclusions that I came up with, and that was also corroborated by data that Gregor McFarlane produced, was that at least 500 feet is needed to attenuate wakes and wave energy from surf boats until the wave is an adequate size where it's approaching the background conditions of what you see on the lake. This is 300 feet more than other boats. So if you've determined that your typical boat needs a 300-foot no wake zone to protect your resources on your lake, then you're looking at potentially an 800-foot or more no wake zone for wake surf boats. And this is important when coming up with regulations. A lot of industry people out there are aiming for a one-size-fits-all solution for no wake zones, and the number they've come up with is 200 feet. Their own research doesn't corroborate this data, and much of the other research that I've collected and data from other universities out there also does not corroborate this 200-foot no wake zone. So the final portion of my study, I looked at wake boat slipstreams. I was unable to procure the equipment I needed to actually physically measure these slipstreams, but fortunately there are a lot of models out there. The theoretical basis for this study were computational models developed by researchers with the Department of Civil Engineering at Pennsylvania State University and the Department of Civil Engineering at Clemson University. Their work focused on the simulations of turbulent non-buoyant jets, and they later validated their work in field studies. Both parties independently developed equations for growth rates and mean velocity decay along the streamwise axis of the jet, and that's how I produced my models. Much of the research has shown that these turbulent non-buoyant jets, they develop in predictable ways. After the initial zone of establishment, there you can see in this picture by the plane of orifice, the jet expands rapidly along the x-axis and at a pretty consistent 11.8 degrees. Velocity profiles across the slipstream exhibit consistent distributions, and there's a lot of formulaic models to look at how those distributions and velocities drop off as it reaches the margins of the zone of establishment. So to collect the data I needed to determine the initial slipstream velocity, you need a number of data points from the boats. You need the speed, you need the RPM, and you need a number of factors concerning the propeller. I was able to collect this data myself during boat trials on a 2019 MB Sports F22 Tomcat surf boat. And I also collected a number of data points from boat manufacturers, and I crowdsourced data from boating forums. This crowdsourcing proved to be one of the most effective ways to get data, because a number of boat owners had very comprehensive data sets on the performance of the boats, both under different loading conditions, different environmental conditions, using different propellers, operating at different speeds. And I received more information than I could ever need to make these velocity profiles. At the bottom of the screen here, you can see one of these velocity profiles. This was from a 2016 Malibu LSV 22. And I show these velocity profiles at 3 different trim angles: 0 degrees, 7 degrees, and 15 degrees. This doesn't account for the fact that the propeller coming off the boat is already at a different angle. I determined these degrees by actually looking. I used a hobo pendant accelerometer oriented along the x-axis while I was in a surf boat, and watched how far that boat tilted as it went from no wake into its displacement mode and then back into surfing mode. I found that these boats often operated at a continuous 7 degrees, and sometimes in heavy conditions or when there was heavy ballast in the boat, they could operate at up to 15-degree trim angle. So in these charts, you can see the slipstream velocities. The shaded regions, the dark red indicates velocity of 0.9 meters per second. The blue shaded region indicates velocities of 0.4 meters per second. And the light red shaded region indicates velocities of 0.25 meters per second. I chose these thresholds for a specific reason. I took a sediment analysis around Payette Lake, mostly around the Southwest Basin, and I found that the sand particle size, the largest particles, were kind of a mid-range sand particle size, and they correlated with this 0.25 meters per second. That's enough velocity to disturb these sediments. Whether it's enough to resuspend them is another question. However, those were the biggest sediments in the lake, and as this is a glacial lake, the sediments only get smaller, and much of the sediment on the lake bed is silt. Silt disturbs very easy, and when these sediments get disturbed, that's when we start worrying about sediment and nutrient resuspension, which can then cause algae and cyanobacteria blooms. So as you can see in this third chart here, a boat operating at 15 degrees, this modeling shows that it could affect the water column and the lake bed at over 10 meters deep. All 3 of the models that I developed kind of had that range between 9 and 12 meters, where that velocity of 0.25 meters per second could be affecting the lake bed. So next, I looked at the 300-foot no wake zone boundary. I looked at depths at the 300-foot no wake zone boundary, and because I had a good reference for the 10-meter contour on USGS, I chose that as the depth that I was shooting for. It's a kind of an average of where those slipstream velocity profiles showed that bed sediments could be being disturbed. In the Southwest Basin, I divided the lake into 20 transects, about a quarter-mile long, and in each of those transects, I determined the maximum and minimum distance of shore for the 10-meter contour in relation to the 300-foot no wake zone boundary. In that first graph, you can see that in 13 transects, the lake was shallower than 10 meters at the 300-foot no wake zone boundary. And in 3 of those transects, the lake was shallower than 10 meters across the whole 300-foot no wake zone boundary. For the 6-meter contour, which I also had a reference for, I decided to plug that in. And you can see that even in that, 10 of the transects that I looked at, the lake is shallower than 6 meters at the 300-foot no wake zone boundary. This means that a boat operating totally legally at that wake zone boundary could in fact be disturbing bottom sediments in those areas. So the main takeaway from this was that the turbulence imparted by the modeled slipstreams is sufficient to disturb sediments of the size classes commonly found at Payette Lake at depths regularly encountered at or beyond the 300-foot no-wake zone boundary. So with this information, I started looking at, where and what is an appropriate no-wake zone. I considered not only these environmental factors and the physical properties of the waves themselves, but I looked at social aspects, I looked at economic aspects in the lake, and the fact that that recreation is a huge economic driver in this community. As I said before, the 300-foot no-wake zone boundary likely doesn't provide sufficient protection against accelerated shoreline erosion and nearshore sediment disturbance in Payette Lake. Through my research and looking at all these other factors, I determined that 500 feet would be a more appropriate boundary. And if you really wanted complete protection of the lake shore and the lake bed sediments, a more effective distance would be 800 feet. I chose the 500 feet partly because of social reasons. One, there's a lot of lake traffic, and moving the boundary from 300 feet to 500 feet only decreases usable area by about 7% or less than 200 acres. When you push beyond that 500 feet, usable area starts decreasing substantially. The 500 feet seemed like a happy medium where there was still enough open area in the lake where wake boats could operate, other boats could operate, and that there was still a large, potentially wave-free corridor near the shore where boats could launch, where homeowners could recreate without having waves coming on shore, and where people could paddleboard and kayak and take part in activities that don't necessarily need large waves. Another big implication of this, especially finding about how deep those slipstreams can disturb the water column. Water depth is a highly important factor in defining no-wake zones. What you see from industry studies is that it's just a distance from shore, and that no consideration has been taken into the depth of the water body. As we can see through slipstream modeling and just the way that even surface waves work, depth is very important when determining these no-wake zones. Again, social and economic factors as well as other user groups should be considered when defining no-wake zones. Unless you're looking for a complete environmental total environmental protection, some of these other factors will probably reduce the size of that no-wake zone. And that's something I found just through talking to people that had implemented no-wake zones, who were working on it, talking to community members, talking to other boaters. And finally, as kind of a byproduct of all this, and communicating with a lot of people and researching how regulations have been implemented in other areas, it's become very obvious that regulations should be consistent across a resource area. The first place that comes to my mind is the Willamette River in Oregon, where about a 10-mile section of river is delineated into zones where you can take part in different towed wake sport activities. In only 2 of these zones currently, you can operate a wake surf boat. This has created confusion among users, and it's created an enforcement nightmare for the authorities. And frankly, the authorities don't enforce anything. And this is pretty consistent where you see those differing regulations for different user types. Having worked in recreation management for many years with the federal government, and now looking at these, it's become very clear to me that regulations should be consistent across a resource area. A lot of the non-wake surf boaters will say, oh, well, we don't create as much of an impact as the wake surf boaters, so we shouldn't have to abide by those rules. But again, that creates not only an enforcement nightmare, but it's hard to educate and it's hard to get people to comply with those regulations. So at the end of the day, it's best to have those consistent regulations. And that's kind of the gist of my research. It's what I wanted to walk you through and show you how these tools and this data can be used to develop an effective no-wake zone that not only takes into account environmental considerations, but the social and economic factors as well. Thank you all for listening, and I can definitely take some questions, and there's my contact information if you'd like to email me questions or look at some of the other work that I've done over the years. And yeah, I'll turn it over to whoever wants to talk.
All right. Thanks, Alex. I'm going to start with a question from, there's kind of 2 related ones. One specific is, are wind wave and motorized boat wave heights, are they additive? And then on top of that, or connected to that, is there an additive effect of wave energy produced by multiple wake boats at the same time in location?
Yeah. This is a really tough subject. Physicists have been looking at this for a lot of years. A lot of what determines whether waves can build on each other is the angle of incidence and what angles these waves are approaching at each other. Because again, not a ton of research has been done in this area, and the variables are so diverse and there's so many variables involved in that. It's hard to say how additive, how waves can add on to each other, how they can amplify each other's energy. I did not look into, as I previously stated, I didn't look into wave energy at all for this project. That's a whole nother science, a whole nother level. That could be a whole nother graduate thesis in and of itself in this topic. It's a very complex study. If you do want to know more about wave energy, I would refer you to the work that Gregor McFarlane's been doing on the Willamette River. It's easily searchable. He's with the University of Tasmania, and he is starting to take a deep dive into the difference in wave energies between wind waves and wake surf boat waves.
All right, great, thanks. Do you have any thoughts on how fishing boats with large motors that are close to shore and their comparative impacts to wake boats, which sit lower in the water but are usually farther away from the shore?
Yeah, so waves aren't just one of the big factors that determines wave height is the displacement of the boat. So a large fishing boat with huge displacement is by its nature, and depending on what speed it's operating in, it's gonna produce a large wave. If you're talking about like a little, just outboard motor, maybe bass fishing boat or something operating close to shore, that's likely not to produce a very big wave, partly because of the ways that the boat's operating, the speeds it's operating at, the displacement, the length of the boat. As I mentioned, when you compare wake surf boats to many other types of motorized watercraft, and that includes party barges, outboard jet boats, water ski boats, it typically takes about 500 feet for the wake surf wave to dissipate to the size of a wake created by another type of motorized watercraft. So part of this, and this is something that Brian was talking about, is because of the way these boats are operated. These boats are operated in full displacement mode where they're plowing water in front of them and making the greatest wake possible. Most other boaters don't operate in this mode, partly because it's fuel intensive. I mean, that's one great way to burn up all your fuel right there, is to operate in that mode. So also tubers and water skiers and wakeboarders, they need to go faster than that. So you see those boats operating in planing mode rather than displacement mode.
Okay. Oh, here's a fun one. Have you been approached by wake boat manufacturers that dispute your data or to interfere with its distribution? Have other states shown any interest in the data, given the widespread and relatively new attention to these issues on natural lakes?
Yeah, so I can say for a fact that members of the Wake Sport Industry Association and members of the National Marine Manufacturer Association have seen my research and have looked at my data. I'm in direct contact with some of them. My data has not been disputed to this date. This was not the most rigorous scientific study, and that was part of the it was never intended to be. This was intended to be a preliminary look for policymakers in the McCall and Valley County area, with more research forthcoming. I offered a number of further research areas that needed to be looked at to kind of corroborate and to make sure that some of this data was in fact something important. And this has been taken up by the University of Idaho. And right now, graduate students at the University of Idaho are conducting more research over the next 2 summers at Payette Lake. One of these is using Doppler imaging to long-term image certain areas of the lakeshore so we can actually see erosion in real time.
Oh, that's great.
One of the other limitations of my work is that the data that the models produced for the slipstream modeling were produced sometime in the past, and they may not have relevance to the higher, they might not be as relevant or as accurate for the higher horsepower boats that we're seeing today. But again, these were the only valid and current models that were even anywhere near effective for this type of modeling. Direct measurements are being taken right now with underwater sensing equipment, looking at this in the Midwest region, and I'm actually eagerly awaiting the results of that research to see how they corroborate my data or if they don't.
Great. And for those people that are interested in finding out more about this data, I'm sure that the Shoreline Partnership will stay connected, and we'll be posting, try as much as we can, provide information on where you can get that information.
Yeah, absolutely.
Next question is, how important are like direction changes with the slipstream measurements?
As the boat changes direction?
That yeah, specifically turns, like as the boats are turning, does that impact the slipstream measurements?
That's a great question. That's a great question that I have not investigated at all.
All right, more for you to do.
Mm-hmm. This is an endless work.
Yep. The more we know, the more we find out we don't know. Okay. Let's see. Oops, I wanted to go back up to this one. Is the 300-foot no wakes zone on Payette Lake, is it a state or local ordinance, or is there like a lake specific recommended guideline?
Yeah, so that's a tricky subject at the moment. There's the statute, the group with authority was disbanded a number of years ago, and we're trying to rebuild some group of statutory authority to make recommendations for Payette Lake. Neither the city of McCall or Valley County have the ability to make those regulations, and right now it falls with the state legislature. Our legislature is very unwilling to act on anything like this, and they are also have seen unwilling to appoint any kind of advisory or regulatory board to take on this matter. We have a number of lobbyists in Idaho and nonprofit groups right now working on that to try and reinstate some kind of body with legislative authority to be able to make recommendations and to change potentially the no wake zone in Payette Lake. At this time, that's still in the works.
So the no wake zone was set at the state level then, but there's nobody overseeing it. Is that?
That is correct. Yes.
Okay.
Yep.
Okay. Let's see. Next one. So was your recommendation for expanding the no wake zone for all watercraft, or for establishing a no enhanced wake zone outside the 300-foot existing no wake zone?
As I said, I believe that regulations should be consistent across a resource area. And for that, I recommended expanding the no wake zone for all motorized watercraft to 500 feet. As I said, that was a happy medium. If you were looking at wake boats specifically, I would have put that to 800 feet. However, as I said before, given the social resources, given the use in the lake, given how much lake would be decreased by moving that from 500 feet to another 800 feet, how much user area would be decreased, I chose to stick with one 500-foot no wake zone for the entire lake.
Mm-hmm. Okay, so kind of following along that one, somebody that lives on a shallow lake, there's some areas are about 30 feet deep, but most areas are only like 5 to 10 feet deep. Mm-hmm. How deep do you think a lake should be before allowing wake boats?
That's a great question. If you just have a little 30-foot deep strip right down the middle of your lake that allows that's deep enough for a wake boat to potentially operate in, that's great. But then you have to look at how those wakes affect as they move towards shore? How narrow is the lake? How wide is the lake? Does it have a very deep bottom with very vertical walls, or is it plain out shallow, like you're talking about, get shallow at the shore? There's a lot of these different parameters we have to look at. And, for these shallow lakes, 30 feet and under, in narrow and small, I would recommend no wake boats operating on those lakes.
Okay, let's see. Do you know yet of any model regulations or that have been used for wakeboard use that have, are there people working on or have established something that is effective?
Well, it's still a work in progress, and effectiveness is a subjective measure based on who's looking at the effectiveness. In my opinion, there have been some effective regulations in the lower Willamette, in an area that's the Willamette River in Oregon. I'm sure many of you are probably not familiar with it. It's a fairly wide river. It's up to 400 to 600 feet across in many places, and it's quite deep too. There's a lot of bank shore development, both residential and commercial, and there's a lot of other users. In the lower Willamette River, they just banned wake surf boats entirely. I felt that was a responsible approach to the problems that they are facing down there, especially with the narrowness of the river. You're looking at pretty heavy shoreline erosion and the potential for accelerated shoreline erosion just because of these large waves being able to reach the shore. A number of other places in Oregon have also banned wake boats. Lake Oswego banned them simply because user conflict, because of extensive shoreline development, and there was a lot of evidence that there was shoreline infrastructure damage on Lake Oswego. So okay. I don't think wake surf boats need to be banned, but I do in many waterways, but I do think that they need to be regulated more effectively with more of an eye towards these environmental considerations.
Okay. Here's just an interesting one. Have you looked at like pontoon waves in any of your research, since they also displace a significant amount of water?
I'm not familiar with what kind of boat that is. A pontoon boat? Yeah. We have pontoon boats in Payette Lake. We call them party barges. And they tow around tubers. And yeah, I did. The wakes from those party barges, often because they're traveling in planing mode, even though it sounds weird for a party barge to travel in plane mode. They travel in plane mode, and those party barges don't make very big waves.
Okay. Let's see. What are your thoughts on the best way to compare the impacts of 1 hour's worth of wake boat waves with a 36-hour windstorm?
I get asked questions like this a lot. It's, again, wave energy is a really hard thing to calculate. One thing I like to think about is the size of these waves. You can look at a coastline that gets battered by waves all year long. Very little evidence of erosion or change, and one tsunami comes through with 2 or 3 waves and everything changes. So wave energy, because it's a function of wave height, as much as anything, it's hard to make these comparisons. It's also hard to make these long-term temporal comparisons across a large piece of lakeshore. There's so many dynamics and so many variables involved. Basic physics, though, tells us that the larger waves are going to be more destructive than the smaller waves. Furthermore, when you look at a natural wind wave regime on a body of water, the lakeshore and the shoreline is usually hardened and resilient to where those natural waves are hitting. It's when we see these bigger waves that are overcoming those natural waves, that's when we see the excessive erosion. That's when we see larger rocks moving off the seashore. A lot of these lakes have I don't want to say have reached a point of equilibrium on the lakeshore, but they're potentially approaching that, where they've been naturally conditioned to the natural wave regimes on the lake.
Yeah, and I would add on that as well. In a windstorm, a certain lake is only going to be able to create a certain size of waves, and that is probably something that a lake has seen like over time anyways. And if the lake has, you know, built up that resilient shoreline that Brian was talking about as well, it's a natural approach. And the other thing to understand is like lakes don't not change. They are constantly changing. It's just this difference between accelerated erosion and natural erosion. And when we start looking at what are these causes of accelerated erosion, one of these aspects is this change in the wave regime. And is it something that a lake has not seen before? And in this case, from a wake boat on a lake, and particularly on a smaller lake, these waves are going much deeper than natural waves would go, and they're creating much more energy. And that is not necessarily sustainable to a lake, and it's going to end up causing accelerated erosion because it's not something a lake has seen before.
Yeah. Yep, that's all correct. And in addition to the slipstream impacts from boats that can scour bottom sediments, because the wavelength of these boat created waves are so much longer, they influence way deeper in the depth in the water column. So as they approach shore, they're also dragging on the bottom from a way deeper place than the natural wind waves do. So there's that effect of bottom scouring too with these boat wakes.
Yeah, and somebody brings up a good point here too, that weather patterns have changed, particularly on storm intensity and duration as well to climate change. And that is a good point. So those waves are going to be impacting. So potentially the size of waves on inland lakes would change. However, a lot of human impacts have changed the system anyway. So lakes aren't as resilient. But on natural lakes, lakes change over time based on a lot of different factors.
Yep, they do. And one of the recommendations I made to the city council and the McCall is to start a long-term environmental monitoring project on the lake. Everything from, you know, wind and wind waves to nutrient monitoring and temperature monitoring, most importantly. So in the face of climate change.
Here's one. Curious to know if the no-wake law specifies what size, if any, wave should not be present in the zone relative to shoreline protection. I don't think so, but I'll let you answer.
Yeah, no, within 300 feet, it's no wakes. You have to operate, I think, below 5 miles an hour even. You cannot produce a wake. Outside of 300 feet, you can do whatever you want. All that being said, there is next to zero enforcement on our lake. The authorities take an education approach, if they take any approach at all. I do not know of a single person ever getting ticketed for operating in the no wake zone in Payette Lake. And as I said, one of my days of monitoring, over 30% of the boats were creating a wake, operating within the no wake zone. The sheriff was sitting not 300 meters upshore watching all of it happen and did nothing about it. So it's telling about how the social aspects of this really come into play when you start looking at regulation and enforcement.
Yeah, and I'll add with regards to Michigan, the no-wake laws weren't really implemented with regards to shoreline protection. It was really from a human safety standpoint. So the concept from the shoreline protection hasn't really been implemented at this stage yet.
And that's a great point too, is you see these 300-foot no wake zone boundaries, and now you have the industry association saying a 200-foot no wake zone boundary. Well, we have docks in Payette Lake that extend over 200 feet into the lake. So, you know, where does that come into play? Is it 200 feet around the end of structures, or is it, how do you calculate for all those factors as well?
Is there a great difference in wakes from wake surfing during the start from the riding compared to once they get going?
Not really. What you see is as the boat goes from 0 speed up into its displacement mode, you see it reach a critical angle of about 15 degrees. I didn't see many boats come off higher than that. And then once it gets up to the horsepower and speed it needs, that trim angle tapers off to a little bit to that 7 to 10 degree range. but it seems like the RPM and the RPM to speed ratio curves are fairly consistent through there. It is during that time when it's accelerating into displacement mode that you see RPM rising fastest in relation to speed, and that's when you have the biggest slipstream velocity profile, when the RPMs are revving up really high, but the speed's not getting very much faster.
Yeah.
That indicates there's a lot of power coming through that motor, but it's not propelling the boat that much.
Are you aware of any studies that might correlate increased wakeboard boat use with increased algae blooms? So, the relation to storing up the bottom sediments more intensely?
I can't think of any with wake surf boats specifically, and that's partly because wake surf boats are so new to the scene. There has been a lot of research done over the years, and a seminal study was done called Stirring Up Bottom Sediments, Resuspension of, or it was called Stirring Up Trouble, Resuspension of Bottom Sediments by Motorized Watercraft. I forget who the author is right now. It's easy to search if you type in Stirring Up Trouble. And that was some of the first evidence that, hey, the prop wash from these boats is stirring up sediments and releasing nutrients. They actually physically looked at nutrient levels after boat passages and documented elevated levels of nutrients after boat passage.
Okay, is wave height some kind of like a workable criterion for regulations? For example, prohibiting wakes that are greater than 9 inches within certain zones? Like when you're talking about implementing regulations, is that something that ends up being integrated and discussed in those guidelines? Or is it just based on like speed and? Okay.
Absolutely. Again, in the Willamette River, in another section, the Newburgh Pool, they're looking at that right now. I've been working with a group over there, the Oregon River Safety and Preservation Alliance, to push through some legislation limiting the size of wake boats to 4,000 pounds. They did a survey of boat owners out there, and they found that that the average size of boats that people were operating were just over 4,000 pounds. And then as you got up into that 10,000 pound range, the number of boat users really dropped off. Again, since displacement is a huge factor in how big waves are created, and weight causes displacement, limiting the weight of the boats can limit the displacement and therefore the size of the wakes being created. All that being said, there's all these aftermarket devices to make your wave bigger. The little fins off the back of your boat, the ballast bags, all that. Those things are really hard to control for at this time. And that's one of the reasons that regulations have been so hard to implement.
Okay, do you have any information on like whether or not motorized boats contribute to oxygen levels in the lakes?
I did not look into that at all.
Okay.
There is information about there out there, and that is a valid concern, and that information does exist.
Okay. All right. I think one thing, have you noticed that if more likely visitors to that lake would be more of an issue than the property owners? Is that something that you even looked at?
Yeah, so that's a great question. In the McCall impact area, there's about 3,000 residents and there's over 10,000 homes. We are a tourist town, and only about 1 in 3 or 1 in 4 of our homes are occupied year round. It's hard to say. There are a lot of locals that own wake surf boats, and there's a lot of non-residents that also own wake surf boats, and there's multiple rental agencies around where you can just rent a wake surf boat for the day. It's hard to delineate between who's using these boats and when and where they're using them, really.
Great, thanks.